All right. So the QR code up there is totally not a crypto scam, by the way. All right, that's good. Let's do this. My name is Raniz. I'm here to talk to you about pipeline patterns and anti-patterns. And the reason I do that is because I'm a consultant at a small company called Factor 10. And so I get to see a lot of other people's pipelines, and they almost always bother me. So I end up fixing them while I'm doing whatever I'm actually there to do. So this is my way of being a bit ahead of myself and trying to get you to fix your pipelines before I get to your work. So let's get started, because this is a 50-minute talk, and I only have 40 minutes. So there is some slides. If you notice a discrepancy in the numbering, it's because I cut out some patterns. But let's get started. So the goal here is to reduce 3 things, essentially. And number 1 is frustrations, because pipelines can be very frustrating, and it's not a fun place to be where your pipelines are frustrating you. So how many in here have ever had a pipeline failure that was fixed by pressing retry? Yeah? Does that feel good? I hate that feeling. So we're going to try and fix that if we can. We're also going to try and reduce boredom, because no one likes sitting around waiting for stuff to complete. If we can make our pipelines faster, we get a reduced feedback loop. Reduced feedback loop means we might not have to context switch, which means we're more effective. Development goes better. We probably produce fewer bugs. Everyone's happier. And reducing the time usually also means that we reduce the workload that we're doing. And I don't know if, for those of you who went to the .NET performance talk, being performant means doing less things. So speedy pipelines do less things. Doing less things is also good for the environment. So if we can, we're also going to save the environment. But before getting into the patterns and anti-patterns, I want to address the elephant in the room. And that is, everyone in here is probably using different pipeline platforms. So I'm going to try and be as general as I can. I will show a few examples of the language of pipelines, which is YAML. And those examples are going to be for GitHub pipelines, GitHub Actions. But everything I talk about here, you can apply to Jenkins, Azure Pipelines, GitLab, GitHub, Bitbucket, probably even weird platforms like Amazon Code Build. Probably also Travis CI, Circle CI, Earthly, and Dagger, if you're using those. So let's get straight into it with anti-pattern number 1. The ritual. And this is where your pipeline is doing everything all the time. Regardless of what's happening, it's always doing the same steps. It's a ritual. So it usually starts out like this. You have a PR pipeline that runs before anyone is allowed to merge changes into your main branch. It does some setup, it lints, it tests, and it runs the backend, the frontend, lint tests, and the integration tests. But then you have a bad merge. And you can have bad merges that wasn't caused by merge conflicts. 2 people make changes in the same part of the code. They don't produce a merge conflict, but the app doesn't compile, or there's a bug somewhere that wasn't triggered by the individual PR pipelines. So what ends up is both PRs are passed, you merge them, and then your main branch is now broken. So someone decides we should discover this early, right? So let's just run the same pipeline after merge as well. We run it pre-merge, we run it after merge. But then something changes in the outside world, outside of our control. So our integration tests fail. So now, well, we need to know when we get back on Monday morning if someone has made a change that breaks our app while we're not there. So we run the same pipeline every night to make sure that everything is fine and dandy. We get to work in the morning and say, okay, Siggy broke the build. So Siggy broke something, and now we need to fix it. So that's what we're doing Monday morning. Because now we know this, because we run it nightly. And then our manager comes in and says, hey, I want to test your build. I want to test every build you make. Can I just get something from your builds? Okay, or sure. That's just on a publish step at the end of the pipeline. So now we're doing every PR. We're doing all the tests, all the linting, and publishing an artifact. And then once we merge, we do all the tests, all the linting, and we publish an artifact. And every night, we do all the tests, all the linting, and we publish an artifact. That's a lot of artifacts, and we don't need to publish an artifact after every PR, most likely. We don't need to publish an artifact every night because the code hasn't changed. It's the same artifact we're building every night, which is kind of unnecessary. But we also probably don't need to run on the nightlies. We probably don't need to run the backend tests and the front-end tests because those should be unit tests which are completely isolated, not affected by the outside world. And the same goes when we merge domain. Maybe we don't need to run the lint because it's quite uncommon that you merge stuff and you get a new lint error. You might get a test failure or a compilation failure, but a lint error is very, very uncommon. So what we should do is we should do the right pipeline for the right job. So on PRs, we run all our tests, all our lints, but we don't publish an artifact. On merge domain, we do the setup, we run the tests, and we publish an artifact. And nightly, we just run the integration tests, because that's the thing that breaks when no one touches the code. So this mostly saves the environment, right? And we can go one step further with this. We can implement this with, and we can go one step further by using conditional pipeline steps, which is pattern number 2. So if we take a look at the PR pipeline here, we have our backend setup, we do backend linting, backend testing. Then we do front-end setup, we do front-end linting, and front-end testing. And then we do the integration tests. But what if you make a backend-only change? Or a front-end-only change? You add a new database index. You change the functionality or placement of a button in the user interface. There's no need to rerun the front-end tests and front-end lint if you haven't changed the front-end, right? Same thing with the backend. If you haven't changed the backend, why are we running all the database tests if you only moved the position of a button in the front end? That's pointless. So we can just skip those. Here we have a hide the settings menu when logged out. That obviously shouldn't be shown, but there's no need to rerun the backend tests for that change because it hasn't changed the backend. And the same thing down here. We had a new index on the user birth date in the backend. There's no need to rerun the front-end test for that because it doesn't affect anything in the front end. We should still run the integration tests in both cases because the integration tests may very well have been affected. But we don't need to run the backend and front-end changes, the tests, if those hasn't actually changed. So here comes the first GitHub Actions example, and this is how you implement this. And where this is GitHub Actions YAML, the technique for doing this is exactly the same in all the other YAML-based pipeline platforms. So the first thing we define up here is a paths filter, where we use a specific task that checks whatever files have changed in this branch. So it figures out all the changed files in this pull request, and then we provide it with filters up here where we say, if anything in the backend directory has changed, then we consider the backend component changed. And we do the same for the front end. And this sets outputs on this task, on this step. And we can forward those to the job by this snippet up here, where we just basically say the outputs of this task, of this job, the backend should be the output of the filter step. And the same for the front end. And now when we have done this, so this runs before the rest of your pipeline, we can now depend on this step in our build step. We can say that we need the paths filter for our PR checks. And we can now depend on this. We can see if backend has actually changed, then we run this step. And if it hasn't, it's skipped. So this means that the files we change can affect what steps we actually run in our pipeline, which both saves the environment and our time. So on to pattern number 3, or anti-pattern number 3, the aestet. So this is where you have natural ordering of your pipelines instead of the practical ordering. I fall into this trap myself a lot when I set up new pipelines. So here's an example of a natural pipeline. So we have first we have a setup step. We do linting, compiling, unit testing, integration tests, and then end-to-end tests, because it kind of makes sense. We start with linting because that's a fairly lightweight thing to do. We then compile, because you need to compile your application, otherwise you can't test it. We then do the unit tests, which are quick, the integration tests, which are a bit slower, and we finish off with the end-to-end tests. We basically traverse the testing pyramid from bottom to top. But when I develop, usually, this is where stuff fails. If my pipeline fails, it's usually the integration tests. Because I do test-driven development, which means I always run all my unit tests whenever I write code. I essentially don't write code unless I have already run all the unit tests, and I don't commit unless all the unit tests pass. I might actually even have that as a pre-commit hook. So those never fail. Linting failures are also fairly uncommon, depending on what language I'm in. In Rust, I usually compile with the linter, so it doesn't compile if I have linting errors, basically. So the integration test is what fails. So in this case, my PR pipeline fails after 13 minutes and 37 seconds. But if I were to put the integration tests first, or as soon as possible, the failure comes as quickly as possible. The most frequent failure comes as quickly as possible. Question? You can, but then you need to compile in parallel as well. So you're going to spend 15 minutes compiling in 3 parallel pipelines. We'll get there. So we'll run the integration test as early as possible, because that's what mostly fails. It will still take us the full pipeline before we get a green check. But we get the failure information on average earlier, which saves our time and might prevent us from making context switches. So, anti-pattern number 4, and this one's for you then. The one pipeline. One pipeline to rule them all, one pipeline to bind them, and it was too long ago since I read the books, so I don't remember more. But this is where we have one pipeline. It might look like this. We have a backend step. We do setup, linting, compiling, testing. And the same for the front end, setup, linting, compilation, testing. And then we run the integration tests at the end. I have an example that I actually ran this on. So this is the crates.io source code, which is the dependency repository for Rust. And it's not their pipeline. I made up the pipeline for the purpose of this talk. But it's a fairly common pipeline. It's linear. It does all the things you need to do to check the code. It runs in 24 minutes and 40 seconds on average, with all the individual steps taking this amount of time. So what we can do is we can split it into parallel pipelines. We can do the front end on its own. We can do the back end on its own. And then we just do one for the integration tests. And now we get feedback after 14 minutes and 50 seconds, which is 9 minutes less than before. But we also add on an additional 8 minutes because we're doing the backend compilation and the front-end compilation twice in parallel. But we can improve on this. We can use pipeline artifacts. So we can make pipelines that depend on other pipelines. So if we structure it like this instead, we have a backend pipeline. We do a backend setup. We do a backend lint, a backend compile, and tests and publish an artifact. So once the backend is OK, we publish an artifact. We also have the front-end setup. We do the front-end setup, lint, compile, tests, and then we publish the front-end artifact. And once we have both of these artifacts, we run the integration tests on the published artifacts. So we avoid compiling the backend and the front-end twice. And this has more or less the same runtime in total as the first pipeline, but it finishes 8 minutes earlier. So we saved 8 minutes without essentially doing anything wasteful in parallel. We're only doing every step once, and we reuse the results between. But we can actually improve on this one as well. So we can move the integration tests, because we want the integration tests to fail as quickly as possible, right? So we can move them back, and we can add on 2 testing pipelines. So in this case, we only compile and publish the front end and back end. We can then branch out into 3 parallel pipelines, where we have one that runs the integration tests, one that runs the backend lint, and one that runs the backend checks, and one that runs the front end checks. So now we're getting feedback after 12 minutes, and we're still only doing the same amount of work as before. So we haven't actually added on that much time. There is going to be some queue times and setup times and triggering times and downloading and uploading artifacts here, but it's negligible in a standard pipeline. So I think this is one of the most important things you can do with your pipelines. Look and see how you can parallelize them. And of course, this also comes with limits, depending on where you're running. So if you're running this on a single on-prem server, there's no point in parallelizing it, because it will just be stuck waiting in queues for all the other steps to complete. But if you're running in a cloud, like GitHub Actions, GitLab CI, or Azure DevOps, where you can have essentially infinite parallelization, you can parallelize as much as possible. Just try to be reasonable that you're not doing too much rework, because that will cost you money and will also waste environmental resources. So, anti-pattern number 5, gift wrapping. This is where you use tasks, like task definitions, instead of actually calling your command line tools. So I have an example here. This is a fictive task. I actually found out yesterday that there is an actual task like this, but it's for Go. It's not for Rust. I haven't updated my slides. So this is an example of how it can work. Someone wrote a action for running cargo, the Rust build tool. We specify we want to run the build command for the release target on the whole workspace with all the features. Nice. But then we want to, for some reason, control the number of parallel jobs that cargo is using. But whoever wrote this library, they didn't think someone would ever use that parameter, so they haven't implemented support for it. So you can't actually pass the jobs parameter to this action. But luckily, they added an escape hatch for adding on arbitrary arguments. So they added arguments. So now we have a nice mix of YAML attributes and then a catch-all for where we just put in bash arguments. If you're lucky. If you're unlucky, whoever implemented this doesn't have that escape hatch and you're stuck. But it's also a bit confusing, and you don't have any control over what order these switches are passed to the final call, because whatever all this does in the end is just construct a command line that calls the command line tool for you. So I think you should just call the command line tool yourself. And since this is a YAML, we can use YAML multiline, which, by the way, has its own website because it's so complex, to structure it like this. So I think this is probably even more readable than what's on top. And you have complete control over whatever command you're calling, the order, and all the switches. If everything goes well, these are equivalent. If you're unlucky, whatever's on top there has inbuilt magic that does things that you're probably not counting on. That happened to me when I used the .NET task in Azure Pipelines. It added on a few commands, which meant that stuff didn't end up on the file system where I was expecting it to be, and I couldn't find it. So we switched to just calling the .NET command line on its own, and everything started working. So yeah, don't use wrapper tasks. I'm not saying you shouldn't use tasks. So, for example, setup tasks is a really good idea. This is from one of my Python pipelines. where I use someone else's task to set up both Python and Poetry. Poetry is a build tool for Python. And then in the end, I just run Poetry, the command line tool, as a command line tool. But I use the tasks to set it up, because I don't want to call arbitrary shell scripts when there is a perfectly fine setup task that does that for me. Downloading stuff and installing them. Also adding them to the path, which can be a problem in certain platforms. So let's go on. Antipattern number 6. It's complicated. And this is where the pipeline is its own software project. I saw this as a customer. This is very much based on that customer. So they had a Jenkins pipeline that lived in its own repository and was published as jar files, uploaded to Jenkins, and then used in all their pipelines. It was about 5,000 lines of Groovy code, and it read an XML file to figure out what it should do on every build. So this XML file contained everything from whatever testing framework they used to the credentials to publish stuff to their production system. I wanted to change something, which meant I had to make a pull request to the pipeline library, wait for that to build, upload the new jar file to Jenkins, update the pipeline to use the new Jenkins library, because you point out the version up there, and then I could try if the changes to my pipeline actually worked, and they didn't, so I had to read all the things again. Horrible. And we'll get to another reason why this is horrible shortly, but I've actually had people tell me that they don't agree with this because this is their job, maintaining pipelines like this. I'm not saying that job shouldn't exist, but I think there's a better way of achieving this, and I think it's to do composable pipelines or composable pipeline libraries. And this is where you write these small snippets that does standard things that you usually do within your company, maybe. And you can share them between teams. So in this case, we have a Rust test, compile and test Rust tasks that does things for us. They might upload the results to, or publish the test results. They might set up credentials to talk with an internal repository or things like that you need to do that is common to all your projects. And you can also have, for example, down here we have an example with a parameter where you can parameterize your pipeline library. So you can add arguments basically to make it do different things depending on inputs to control what happens. And once you have this, you can go one step further and you can write actual pipeline definitions that are reusable. So in this case, if you're running a company standard Rust pipeline, you can just use the entire Rust workflow instead of composing the pipeline yourself. But the major point here and the big bonus is that if this doesn't work for you, you can go back to this and you can you can replace stuff and you can put stuff in between these steps to do as little custom work as possible and reuse as much as possible, but you're not locked into this, or for that matter, this. So that's what I think you should do. And another example why you really shouldn't write 5,000 lines of Groovy Jenkins code is because that entangles you into Jenkins. You're not migrating away that pipeline anytime soon. And this might happen with whatever platform you're using. If you start writing applications in your pipeline, whenever something better comes along, you're in a bad position. GitHub Actions, GitLab, CI, Atlassian, Bitbucket pipelines, Azure DevOps, they all look pretty good right now, but on the other hand, Jenkins was really nice 10 years ago. But I don't think anyone is starting new projects on Jenkins today. But there's a lot of people trying to migrate away from it, and they're stuck because they have 5,000 lines of Groovy code. So what should you do instead? Well, you should use something that isn't your pipeline system, that you can easily transfer. And what you pick, I'm not opinionated about that. I tend to use Bash and Make because I'm a Linux freak. But this is from my the same Python pipeline as before. We do the setup of Python, poetry, and then we just run make in it. So we offload all the logic to make. We're just using GitHub Actions to run make for us. And the make file looks like this. It's pretty unimportant, but we have a CI target, which in turn depends on style check, linting, type checking, and testing. So in this case, we just run make CI, and make makes sure that it runs all the commands that actually we want to check in GitHub. And the nice thing about this is that when I develop locally, if I want to test my CI pipeline, I just run make CI on my terminal, and I run the exact same checks that would be run on GitHub Actions. Because I don't know if you've noticed this, but debugging pipelines is quite time-consuming because there is not really a good way of running them locally. You need to push something, have the pipeline run, wait for the build system to kick in, and then you, maybe if you're lucky, 5 minutes later, you have a result, and then you need to do it all again. There are tools that can run locally. I know there's a project for running GitHub Actions locally, but I've never gotten it to work with any of my pipelines. Antipattern number 7, Groundhog Day. How many have seen the movie? Fewer than I was expecting, actually. So then you don't know what this is about. So this is when you start from scratch all the time. And basically, bog standard pipeline. We have some setup, we fetch dependencies, we lint, we compile, and we do tests. Could be essentially any pipeline in any reasonably simple software project. How many people in here cache stuff in their pipelines? How many people in here only cache their dependencies? So that's the most common thing that people cache. You see some snippets. In an example, you add your npm cache directory. You download that, upload that. Everything goes a lot quicker, right? So the idea is that instead of just downloading all the dependencies, which is extremely slow, we restore the cache, and then we need to make sure that we got all the dependencies because something might have changed. We might have gotten an old version of the cache. And then if something changed, we upload a new cache at the end. The thing is, the internet is kind of fast these days. So this is the same crates.io application, the Rust side. There's around 80 dependencies to download. It takes around 7 seconds. There's not much to save here. We do save something. We do save around 1.5 seconds by caching it. There are other benefits to caching, which is that we are not dependent on an internet connection. We can still get all our dependencies locally. So I'm not saying don't cache your dependencies. I'm just saying that there are bigger fish to fry. And that is build output. So instead of just focusing on the dependencies, we focus on the compilation. So we focus on the lint, the compilation, and the tests. And we surround this with caching. And this only works for languages that are incrementally compiled. Rust, Java, .NET. .NET isn't a language, but you get the idea. C, C++, probably Swift. I think you can do it in TypeScript, but I don't think it's on by default. It doesn't work for CSS precompilers and stuff like that. But if we apply this to the Rust pipeline, the crates.io backend, we have linting without caching takes 2.5 minutes, compilation takes 5.5, and then the testing takes around 3 minutes. But if we add caching, Rust only needs to, so this basically turns into what you do when you're developing locally, when you rerun the compilation. Everything is already compiled, so the linting step only needs to lint the new code, which takes 24 seconds instead of 2.5 minutes. And the compilation only needs to compile your new changes plus whatever is reliant on those changes, so it kind of cascades away. So depending on where you change, but importantly, it does not have to compile all your 80 dependencies again, because that's already compiled, and your changes probably doesn't touch those. And then, of course, the tests. You shouldn't cache your tests. so they are rerun, all of them. And this saves us almost 4.5 minutes of build time by caching around 2 gigabytes of data, which takes 30 seconds to upload and download. Well worth it. There's another thing we can cache, which is container images. If you're using Docker, this requires build X. If you're using Podman has this built in. But we tell Docker or Podman to use a specific image as a cache. It can't be the same image that you're building because it's different information stored in here. But I usually just tack on a suffix and call it cache. So what happens here is that whenever the build is supposed to do a step, it checks with the remote cache. If you're using Docker locally, you do it all the time, right? You change something in your Docker file or something in the files that go into your Docker file, and Docker kind of fast forwards to wherever that change happened, reuses all the images up to that point, and goes on from there. So this is the same thing, but it's for remote images. So when you do this on typical ephemeral build systems, which is the norm today, I'd say, unless you're running on-prem, you start from scratch, so there is no local Docker cache that you can utilize. And so we just pointed to a remote Docker cache, and it does the same thing. So in the example down here, we install Leptos, which is a front-end framework for Rust. That takes 6 minutes to build. But in this case, it's already been cached, so it takes 8 seconds to download and check. And then we install Cross, which is a cross compiler for Rust. And in this case, that wasn't installed, that wasn't present in the cache, so it actually has to do this step. So it continues on from there. Now this is cascading. So whenever you hit something that hasn't been cached, all the steps after that has to be redone. You can get around this by using multi-stage builds, where you basically build things in parallel, maybe not in parallel, but in different Docker images, and then you tie everything together at the end. It introduces a lot of complexity, but if you have lots of long-running steps that you can parallelize in that way, it might be worth it. Now, when we have caching of container images, we can use this to make tooling images. And this is a fix for these ephemeral builders that doesn't contain any of our tools. Depending on the platform, it can contain a lot of tools, but might not contain the exact tools that you want. So the idea is that we have a pre-step that builds an image, publishes a tooling image, and then we use that tooling image to run the rest of the tests. So now we have all the tools available for backend and integration tests. Could be a specific version of your runtime, could be a specific tool you're using, whatever you need to have installed that isn't there by default. And we can use this with conditional compilation. So whenever main runs, we build the image, we publish this at latest. And then when a build comes around that doesn't change the tooling image in any way, I usually put this in its own directory so it's easy to filter. We just use the latest image that was published by main. Build our stuff, and we're done. When a PR comes around that does change the tooling image, the tooling image step triggers, we publish a new tooling image, and we use that image, the newly built image, to run the rest of the pipeline. And this is really efficient because you're very seldom changing the tools you use. So you're more than likely, I might guess that around 90% of the cases, you will run on the latest image that was built on main, which will speed up your pipelines. But this also opens the opportunity for interference, which is where you collide with other pipelines. And this is typically happens when you have shared resources. So in this case, we have the same setup here. We build an image, but we call it latest. We always publish our built image as latest. So a pipeline starts, builds the image, publishes it. Frontend and backend starts running on this image. Everything goes well. While the backend and frontend pipelines are running, another build starts. and it publishes a new image, overwrites the old tooling image, because they're using the same tag. They're both called latest. So now when we get to the next step, front-end and back-end finishes, build image finish, back-end and front-end starts in the second pipeline. All the integration tests in the old pipeline is running on the wrong image, so they might fail. The pipeline down here will be fine because it's that pipeline's image that we're using, but the old pipeline might break. Yes. Because that's totally not what I'm trying to avoid with this talk. So be sure when you're using shared resources to make sure that everything you use is unique. For Docker images, the commit SHA is probably a good idea to use because I have never seen that collide. The same if you're using shared testing databases. Create temporary databases that doesn't collide. Don't use the same database on all your pipelines. They will bite you eventually. So we have 5 minutes. See if we can finish this in time. Antipattern number 9, overloaded. Don't run your pipelines on Raspberry Pis. So what should you run your pipelines on? I have a few rules of thumb, basically to avoid issues, hopefully. So Raniz rules of thumb for build agent sizing. Number 1, the build agent should be at least as powerful as the least powerful developer machine. So if all your developers are running dual processor Xeons with a terabyte of RAM, your build server should be running on dual Xeons with a terabyte of RAM. If you have some of your developers running on an old Dell XPS 13 with 4 gigs of RAM, and they can run your pipelines or build your program, then you're probably fine doing that on your build systems as well. But ideally, number 2, the build agent should be at least as powerful as the most powerful developer machine. So if your build agent are more powerful than whatever your developers are on, you probably won't have resource problems. But if you're not there, and if the build fails because of a lack of resources, don't spend 4 days trying to optimize to consume 500 megs of less RAM. Just give it more RAM. Give it more processing power, give it a bit more RAM. It's way cheaper in the end. And if the available build agent configurations aren't sufficient for what you're doing, consider at least running your own. So should you run your own build agents? Well, you get full control if you run your own build agents, but you need to maintain them. You can choose exactly the configuration that you want, but you need to manage scaling. This is where the parallelism comes in, right? If you have 400 pipelines running simultaneously, you need 400 build agents. Otherwise, you will have queues, and no one likes queues. And there's a pro and a con, cost. So if you're running your own build agents, it can be a lot cheaper. A VPS at SafeSpring, a Swedish cloud provider, costs 1/10 of what it costs to run the same amount of time on a GitHub Actions server. And actually, GitLab CI is even more expensive. But you need to have someone maintaining them. If you already have that capacity in your company, that might not even be an added cost. If you're a small developer team of 4 people, you're going to spend quite a lot of effort on setting up your build agents. So we have 2 minutes to talk about what's next, which means we have 1 minute for Dagger and 1 minute for Earthly. So these are 2 new tools that I'm quite excited about trying out. Both of them are built on Docker Build Kit. So essentially, they're doing what we did with the Docker image caching, but they do it with your code. So you get caching for free, where if you structure your pipeline so that you download dependencies and then you build your code, if the dependencies hasn't changed, it just reuses the image from where it had already downloaded your dependencies. It's basically fast forward for your pipeline, or emulation save states for your pipeline. Dagger uses programming languages, and I've seen what happens when you give developers Groovy for the pipeline, so I'm not sure that's a good idea. Earthly uses some kind of mix between a Docker file and a make file. which isn't as horrible as it sounds. So, quick recap. Don't be ritualistic about your pipelines. Don't order your pipeline steps according to what feels nice. Be practical and pragmatic about it. Don't have one pipeline that does everything. Don't use gift-wrapped tasks. Whatever this is. Don't complicate stuff too much. Don't start from scratch every time. Try to not interfere with parallel pipelines. Be unique in whatever you use. And don't run your builds on Raspberry Pis. Thank you.